And the first speaker is Henry Lin from Princeton. And I looked at this paper. It's a recent paper. It's very interesting. It seems like some really new ideas about solving unsolvable matrix models. So yeah, so please go ahead. You have half an hour, and since we are quite tight with the schedule, please stick to this time.
Great. Okay, so thank you for the invitation to speak, and I look forward to any discussion that will come up. Today I'm going to be talking about a new method to solving random matrix integrals, and similar methods can be extended to higher dimensions, at least in the case of quantum mechanics, and I'll discuss that at the very end. So the idea of the bootstrap in general, not just the matrix bootstrap, is that inequalities are almost as good as equalities when you have lots of them. The general ingredients of any bootstrap are, number one, a set of restricted data. So in other words, like in the CFT bootstrap, you don't need to talk about all possible correlation functions in space and time. You need to talk about 2-point and 3-point functions. And in particular, they're only defined by some numbers instead of some functions, actually. And the second ingredient is that you need some sort of positive norm. And the third ingredient is that you need some other relation, like crossing, which is not obviously compatible with number two. So the tension between the positive norm and this other relation will give you some sort of non-trivial constraints that allow you to potentially solve the model. So I'm just going to try to apply this philosophy to the case of matrix integrals. And I'm going to now explain to you the three ingredients. So the first ingredient is the truncation to a smaller set of data, right? So in a matrix integral, first let me just define what I mean by a matrix model. I'm talking about integrals of this form. So you could be integrating over several Hermitian matrices, let's say, with some action, which is a polynomial in the matrices. And I'm working in the large n limit where I keep the couplings, the coefficients in the polynomials constant, but I scale n in the way that I indicate here. So the truncation that happens is that at large n, you only need to consider single trace operators, right? You don't need to multi-trace operators factorize. And in particular, you only need to sum planar diagrams when you're trying to compute these types of things. Now, when you meet an integral like this on the street, the first thing you should ask is, does it actually exist? So unlike the case of single variable integrals, it's not clear if the coefficients of the polynomial are positive or negative, whether or not this integral actually makes sense. And in fact, just determining the region in which the integral makes sense is somewhat non-trivial. In general, it's not solvable by analytical techniques. That's the zeroth order question. The first order question is then to determine, of course, the value of observables as a function of the couplings. So when I say that I'm going to solve a matrix integral, I mean essentially this. Now, that was the first ingredient. The second ingredient is positivity constraints. And these are extremely simple in this context. So let phi be some arbitrary superposition of matrices. In a single matrix model, it would just be superpositions of powers of matrices, but more generally, it could involve all possible words, right? Like in a two matrix integral, it would be, for example, phi could be a superposition of A, B, A, B, A, B, A, and some other powers of A and B. And then the requirement is just that trace of phi dagger phi is always positive on expectation, right? Well, it's true without taking the expectation, so when you take the expectation, it has to also be true. And for the single matrix model, I should say that this, in general, leads to a constraint that this cal M matrix, which is the matrix of correlators formed by the Gram matrix formed by taking this inner product, has to be positive semi-definite. So all of its eigenvalues are positive. And for a single matrix model, this basically boils down to the requirement that the eigenvalue density of the matrix has to be positive. But for a more complicated matrix integral involving many matrices, this is a more complicated positivity constraint. Okay, so now I need to explain to you the third ingredient, which is to relate the correlation functions in some way so that we get some interesting constraint that plays with the positivity. So this is very standard. It's just the so-called loop equations, which are also known as the Schwinger-Dyson equations, applied to the matrix integral context. And there's a simple diagrammatic interpretation of them. So if you consider a blob with k external legs, which represents something like trace of m to the k, you can follow any one of the legs into the blob. Okay, So in particular, if you follow one of these lines in, there are two things that can happen. One thing that can happen is that you don't encounter any vertex. Okay, if you don't encounter any vertex, then large N factorization says that you must split the diagram into two pieces, right? So this will give you some sort of double trace term in the matrix integral, and that double trace term will factorize by large N. The second possibility is that it encounters a vertex, in which case it increases the power of the correlation function. So if you started with trace m to the k, you might get trace m to the k plus 2 or whatever, depending on the interaction that you have in your polynomial. Okay, so I'm having a little bit of a technical difficulty right now. Hopefully you can see the slides well. But the interesting thing about the loop equations is that they relate low point functions to higher point functions. So in particular, if you know some of the lower point functions, you can predict the values of many, many, many high point functions. And in fact, even in the multi-matrix case, if you know a finite set of correlation functions, you should be able to use the loop equations to generate an infinite set of correlation functions. All the correlation functions in theory should be determined by these sort of finite initial conditions. So I'm going to call the search space the minimum set of correlators such that the loop equations fully determine the rest of the correlators. And while the search space is not unique, the dimension of the search space should be unique, at least if it's finite, right? Okay, so in the case of the one matrix model, the dimension of the search space is just determined by the degree of the polynomial that enters into the potential. For an M matrix model, it's a little bit more complicated, but we can give a sort of heuristic rough estimate of what the size of the search space is as follows. So if you consider one of these blobs, like I discussed before, there are k external legs, right? So that means that you can follow each line into the blob, and at least naively, you'll get a different equation, depending on which external line you follow in and do the procedure that I described. On the other hand, so that gives you a factor of k. Now, on the other hand, there are m to the k over k single traces, right? So this gives you, roughly speaking, the number of equations. And you see that when k, the number of external lines, becomes of order m to the d, where d is the size of the polynomial, is the highest term in the polynomial, is the degree of the polynomial, you expect to have enough equations and enough unknowns. So this is not supposed to be a very serious argument, but it's supposed to be a heuristic argument that the search space is finite, at least for multi-matrix models. Okay, so now I'm going to just try to apply this technology to the single matrix case first, where we can, of course, analytically solve it. But the idea is to test the constraints and see whether or not you actually get convergence to a solution. So let's start with a very simple matrix model, which is just 1/2 m squared plus a quartic term. And I'm going to assume now that the quartic term is positive. Okay, so in that case, as the coupling increases, the trace m squared, right, will decrease, and that's just because the potential is becoming more confining, right? And so we see that if the green line here is the exact solution, and the gray region is the region that's allowed when you impose a certain number of constraints. In this case, it's a relatively small number, like 4. And as you increase the number of constraints, you get the dark gray region and then the black region, which is converging very quickly to the green line. So I think with only 10 or 12 constraints, you get a very, very fast convergence to this green line. Now, we can also sort of look under the hood and see how are the different constraints being activated. So here, I'm not I'm not enforcing the entire positivity of this cal M, this large gram matrix. I'm simply imposing positivity from single correlators, like trace of an even correlator is positive. So trace of m to the 72nd power is positive. And that gives you some interesting constraint on phase space, or not phase space, but this correlation space. And when you impose many of these different constraints, roughly speaking, you get convergence to this black curve. Okay, another thing that we can study is a matrix integral where the potential is unbounded. So this is a little bit more interesting. So we're going to study the same model, except now with G negative. And I'm only going to impose a few constraints like I did before. And you can see an interesting phenomenon, which is there's a peninsula. And this just means that if I go to a value of G, which is too negative, then I cannot find any solution to the matrix integral. I cannot find any positive solutions. And this is what we expect from the analytic solution. In particular, there's a critical point in this model, which also defines the radius of convergence. And once you go beyond that critical point, the model is ill-defined. So this green curve is the exact solution again. And the point is that imposing a finite number of constraints, you get some bound, you get some lower bound on the critical point. And as you increase the number of constraints, you very rapidly will you will get a very accurate bound on the critical point of this model. In principle, you should also be able to do better and, for example, derive scaling exponents and so forth, which are related to the critical string. So I think this is a point that should be explored further. Now, one more point is the two-cut matrix model. So again, we're setting a quartic model, but with the other sign of the quartic model, and we get the Mexican hat sort of potential, right? And in this model, the interesting thing is that at large n, there's not just a single solution, but there's sort of a one-dimensional line of solutions, right? And that corresponds to the filling fraction, whether you put a certain number of eigenvalues on one side versus the other. And the interesting thing is that just applying this bootstrap philosophy, you see that the gray region doesn't converge now on a point, but it converges on this entire green dimension, this green line. So if we were to include couplings, it would be a two-dimensional region. For a fixed value of the coupling, it's just some one-dimensional line. Now, more generally, this is related to the concept of the search space. So the idea is that the search space is always greater than or equal to the number of filling fractions, which is the number of true solutions to the matrix model. But in general, you can interpret the dimension of the search space as a number of unphysical filling fractions. So to explain this, recall that at large n, the effective action has the form of, you can think of this as some sort of charged particles with some charge density, right, sitting in some potential, but they also experience repulsion. And the point is that if you allow for negative charge density, just formally speaking, you don't impose the constraint that the eigenvalue density is positive. If you allow for negative charge density, well, the particles will, of course, feel the opposite potential. So a local maximum will be felt as a local minimum. So this sort of green region here is where you fill a bunch of anti-eigenvalues. And the point is that there are stable solutions of this form which violate positivity, but otherwise satisfy the loop equations. So the dimension of the search space can still be interpreted in this way. And when we impose positivity, we're simply eliminating all of these negative eigenvalue density regions. So this is a very nice picture for the single matrix model. For the multi-matrix model, of course, we don't know how to write things. I mean, in general, you can't write things in terms of an eigenvalue density. So I don't have a corresponding picture. Now, before we move on to the multi-matrix model, I just want to explain a little bit about why this method actually works in the single matrix integral case. So if you think about now the space of correlation functions of a single matrix, this is some very high dimensional space. Each axis is like trace of m to the k, right? And the positivity constraint says that the allowed region is some cone in this very high dimensional space. Okay, so you would expect that this method works very well if the exact solution to the single matrix integral lies on the boundary of the cone, right? If it lied on the boundary of the cone, then that means that if you were to just be slightly off the exact solution, you would likely, puncture the cone. I mean, you would pass the cone in one of the dimensions, and then you would be in the disallowed region. So we need to explain why the exact solution should lie on the boundary of the cone. Well, that means that there are some nearly zero eigenvalues to this Cal-M matrix, right? If you're on the boundary of the cone, that means that you're barely positive in some sense. And so we need to explain why there should be nearly zero eigenvectors. And turns out that the explanation is pretty simple. So if we know the exact solution for a single matrix integral, we can usually write it as some eigenvalue density, which has some compact support, right? So if the eigenvalue density has some compact support, this means that we can find polynomials which are almost zero in this region, but are non-zero in the regions outside, right? And this polynomial will be an eigenvector which has very, very small eigenvalue. And in particular, when we increase the degree of the polynomial, or in other words, when we increase the amount of correlation functions that we're considering, we'll be able to make a better and better approximation to a zero region in this plot. So in particular, I just plotted the smallest eigenvector for d equals 12 polynomials and d equals 8. And well, you see that the d equals 12, it's very, very close to a 0 eigenvector. So this explains why the matrix, the exact solution lies on the boundary of the cone and why the method should work. You can also see this a little bit more dramatically in the case where there's a double well. So in the double well potential, the eigenvalues are in compact support, but in 2 intervals. And you see that the polynomials avoid very cleanly the regions where the eigenvalues sit. Okay, so now that we have some confidence about the single matrix integral and how it works, let's turn to the multi-matrix integral. So one of the simplest multi-matrix integrals which actually is solvable is the Ising model, and it's a 2-matrix integral with a very simple A-B interaction. Long story short, you can this model is actually very simple to solve, even using the Bootstrap, because the loop equations close on a very small subset of the possible traces. And so we can very efficiently solve this model using the Bootstrap, and it of course agrees with the exact solution. A more complicated model, which as far as I know is not solvable, is this multi-matrix model with interaction of the form AB squared plus BA squared at some particular value of the coupling. So as far as I can tell, this model is not integrable, and nevertheless, we were able to, well, it's not 100% clear that the model has been solved, but there's some evidence, I would say numerical evidence, that the regions are shrinking to a small region, or perhaps a point when you increase the number of constraints. So this is numerically somewhat challenging because, well, the search space is higher whenever you have a multi-matrix integral, so you have to search over maybe a dozen variables or so. And then you also have to calculate a very large matrix because you see the size of the matrix that you're calculating is exponentially growing with the degree of the polynomial in a multi-matrix integral. But in principle, I don't see any obstruction for using this method to solve a fairly general multi-matrix integral with many parameters. It'd just be a sort of computational or practical engineering sort of challenge. Okay, so now I would like to move on a little bit and discuss some future directions. So I mentioned the case of the matrix integral, and well, there are many future directions within this class. So for example, we'd like to understand whether this method can say anything at all about cases where you don't have at least any sort of naive positivity, like if you have fermions or if your couplings are complex or something. I don't know if it can say anything about that. We would also like to know about 1/n corrections to the matrix integral approach. I believe that that should be doable. And just as a sort of fun comment, you can consider the case n equals 1, right? So just doing single integrals with no matrices, just ordinary variables. This same philosophy can solve that with almost no modification. The difference is that instead of considering in the loop equations, right, instead of having a double trace, you will just get there are no such thing as double traces, right? You'll just have AB to some high power, right? So the loop equations are actually linear in the case of n equals 1, when they're just matrix integrals, and you can solve these integrals in this approach. For finite n corrections, there's probably a more involved story. And then we would, of course, like to discuss higher dimensional cases. Perhaps eventually we would like to do something like solve large NQCD, which was discussed in some previous work. So another thing that, so now I would just like to focus on the quantum mechanics discussion. So this is from a paper, Hahn, Hartnell, and Krutoff in the Stanford group, plus some work in progress. So so far what I've been saying has only been using positivity of the measure, right? I've used the fact that when you integrate over Hermitian matrices, the measure is positive. When we go to quantum mechanics, there's an additional type of positivity, which is not the same, which is reflection positivity, right? And that says like, well, I mean, you all know what reflection positivity is, but it says that if you look at this circle, this thermal circle with 4 insertions, that this particular expectation value is positive, for example. And the point is that using this type of positivity, there's no problem with fermions. This is just the positivity of the Hilbert space norm, right? And another nice feature is that there's time translation symmetry. So this, an obvious consequence is that the expectation value of the Hamiltonian, the commutator of the Hamiltonian with any operator is 0. And that might sound a little bit trivial, but if you apply it many, many times, it can give you some non-trivial consequences. Okay, I would just now like to, this is sort of a side comment, but obviously one model which we would like to say something about is supersymmetric quantum mechanics, like a BFSS matrix model. And the obvious generalization of their ideas is to use the fact that in the ground state, the supercharges annihilate the vacuum, right? So you would like to use something like the anti-commutator of the supercharge with any fermionic operator is going to be 0 on expectation. And I would just like to say that if you choose fermionic operators in some very simple way, so for example, if you choose the fermionic operator that you're using this relationship with to be the supercharge itself, you of course just get the constraint that the Hamiltonian is 0 on expectation. If you choose it to be the free supercharge, so the supercharge without the interaction term, then you get this constraint that k, the kinetic term plus, so this is the kinetic term, this is k, this is the potential term, and this is the fermions, right? You get this constraint that k plus f over 2 is equal to 0. And then if you can choose finally the fermionic term to be some, to use x instead of p, you can get some relationship between x and p, which is very close to the uncertainty relation. So using these, just choosing these 3 operators, you get some bound now on the size of the matrices, trace x squared or trace x to the 4th, right? And it turns out that the bound that you get is exactly the Polchinski variable theorem bound, which is not too surprising. So this is the bound that tells you that the size of the matrices is, roughly speaking, the size of the gravity region. And well, a simple question is that this is a lower bound on the size of the matrices. Perhaps by just choosing a few more operators, we can derive an upper bound. So this would really confirm that the size of the matrices is the size of the gravity region, which sounds like a complicated computation from any other perspective. And another thing that we might want to compute is, for example, higher moments of these matrices. So in it's expected that trace of x to some high power doesn't exist. It's infinite. So it'd be nice to show, just using this bootstrap approach, that you can roll out some, any finite value of trace x to the 10 or something. So I think these are perhaps some, the main point of this slide was to say that even though you have a very complicated matrix model with many matrices and fermions and all this stuff, you can still use the bootstrap philosophy to derive some sort of constraint. Of course, whether or not that constraint is going to be powerful enough to actually solve the model is an open question that will definitely have to involve some numerics and so forth, at least from my perspective. So this is pretty much just the appetizer for saying that there could be lots of interesting applications of this type of philosophy. All right, thanks very much. I'm happy to take any questions now.
Thank you. So, who would like to start with some questions?
I can start.
Mm-hmm.
So when I think I asked you recently in a different conference this, but maybe this will be a question also for the audience. When you have this more than one matrix model, you can build various words with them, right? And in n equals 4, we can also write different words with our operators, and we are used to picking nice linear combinations that integrability prefers, that diagonalize, for example, the dilatation operator in the case of the gauge theory. So are there also nice combinations of words in these 2 matrix models? Is there some integrability in that sense of choosing nice words in matrix models or matrix quantum mechanics with more matrices? That would help also pick a better base for this matrix, for example, that you construct.
Yeah, I'm very sympathetic to the question. I don't know the answer. I will say that maybe this method can be used to somehow empirically find these combinations. So maybe you can look at I'm not sure this is the right thing to do, but maybe you can look at the constraints, the particular operators, which give you very tight constraints, and hope that somehow those are somehow a nice superposition of matrices, which are interesting. Yeah, I don't know of any case where you can have, yeah, you know, this sort of nice basis. It's analogous to n=4, but maybe in the case where there are Grassmann integrals in addition to bosonic integrals, maybe there would be something.
I intervene. Of course, the answer is affirmative because for many occasions, like for this Ising model, Matthias, me, Ivan, we actually found, of course, the closed loop equations. I think the first ones have been found by Matthias, and particular finite subset of operators. I mean, not finite, but you take certain combinations of matrices in some powers, and this is enough. A couple of combinations. This is enough to close the loop equations. So for solvability, essentially, you have to find such combinations of these words, simplest combinations, which you can always use as quantities on which the loop equations close.
Is there an interpretation of those words?
Hard to say. For two matrix model, you can find it immediately. Something like traces of first matrix or traces of second matrix or traces of their product in various powers. Something like that. I don't remember, maybe Matthias remembers better, but this is easy to find. Whereas, and it's maybe a continuation to Pedro's question. Indeed, if the model is unsolvable, like your second model, Henry, where you have ab squared plus a squared b, you say that even if it's unsolvable, you can find a finite space of such operators through which you can express all other polynomial operators, yes? And this sounds to me a little bit inconceivable because you have very complicated space of words of two matrices, huge space, and you have only, due to loop equations, due to equations of motion, you have only finite number of combinations through which you express all the rest. But this is a dream usually in quantum field theory. Yes, you can express all physical quantities through finite set of certain simplest physical quantities. Sounds a little bit hard to believe. How do you prove it?
You have to switch on the microphone. Switch back, please. Microphone.
Can you hear me now?
Yeah.
Okay. Yes, I agree that that's remarkable. Maybe first, let me just say something about the Ising model. So yeah, if you, in fact, we use that simplification that you mentioned to solve the Ising model efficiently in the Bootstrap. Yeah, and it comes from the very simple fact that if you draw a Feynman diagram, which involves trace A to some power, B to some other power, then if you just focus on the vertex, the line which goes, let me draw a picture if I can. Yeah. So let's say that you have A in red and B in blue, right? So if you follow in a line which is on the boundary between A and B, right? The worst thing that can happen is that A can be converted into a B. So it still keeps the form of the correlation functions. So the loop equations close exactly on this very small subset correlation functions of the form trace A to the K, B to the A. But of course, I think that's much simpler than like the integrability discussions in n=4 and so forth, where you.
Right. So I would imagine that it would be nice, for example, in these models that have an holographic dual, there should be roughly one combination per string state, right? So it's not, there are many more nice combinations, so roughly the same kind of numbers that we have in n=4, right? So it should be a richer story, I would imagine.
Yeah, I think it has to be more complicated. And well, yeah, another thing to say is that if you had some ansatz somehow for these things, it would be nice because you could somehow plug it into this Bootstrap and try to. Anyways, the other comment, I guess, is yes, I think it's a really strange property that the dimension of the search space is finite. And I should say that I don't know this 100% for sure. So I gave a crude argument for why it should be, but a detailed counting doesn't exist for a variety of somewhat complicated reasons. But empirically, it seems to be true. So if you just put in any potential that you want, you can just try to solve the equations up to some finite degree. And you find that the number of unknowns in this equation is much, much smaller than the total number of correlation functions. And the reason why, I think that the basic reason why that's happening is the reason that I said, which is even though the number of correlation functions is growing exponentially, the number of equations is actually growing a little bit faster than that, right? Because each one of these blobs, you don't just get one equation per blob. If you just got one equation per blob, it would be game over. But you actually get a number of equations that's proportional to the number of external lines that goes into the blob. Every line that you get, every line that you follow in is naively a different equation. Now, I can't make this a very precise argument because you get a lot of degeneracies in some of these equations, right? So in order to understand the counting, you would really need to understand the degeneracies. And I think, yeah, that's it's a very simple theoretical problem that would be good to understand better. I wish I could tell you I wish I could tell you.
By the way, an important comment to the previous discussion. Of course, as usual, there are solvable models, but not all physical quantities in the solvable models are calculable as usual. We know it very well from n=4. Not everything can be computed. So even in Ising model, in two-matrix model, if you take arbitrary word, a trace of arbitrary word of A and B, it's not necessarily computable. Only very particular combinations, which
that's right.
On which the loop equations clause are calculable. So it's another interesting problem, yes, to compute uncalculable, unsolvable operators.
Unsolvable sectors of solvable models.
Sectors, yes, of solvable model.
Yeah. So, well, I think we have to move to the next talk, and then we can have more discussions later in the discussion session. Is it a very short question, Leopoldo? You had a question? Is it a very short one? Or?
Yeah, my question is kind of short, if I may.
Yes.
Yeah, so I was wondering if you can say a little bit about connections with Chern-Simons models, ABJM, these kind of models that can also be solved, but are slightly different, whether your method can say something directly about them?
Yeah, this is something that I've been wondering about. Maybe I'll just turn the question back to you and to the audience, which is whether, yeah, in this integrability discussion, where it's, yeah, in this localization discussion, you usually get these matrix models, which are somewhat complicated. But as far as I know, I don't know a situation where it doesn't reduce down to just eigenvalues or something. So is there some, yeah, can you start with some complicated field theory, which under localization gives you some multi-matrix model, which you can't solve analytically, but you're still interested in its behavior at large n or something. Yeah, that's something that I wonder. So the short answer is I don't know.
Yeah, so it sounds like a perfect thing for the discussion.
Thanks. Thanks.
Yeah, thank you. Okay.